Hey everybody, sorry for the delay with this video. I've actually all day been trying to get the computer fixed so it could record my voice, and hopefully it's doing so now. I've also tried to change the color of this mouse, and I think it should be able to pick up the movement now, hopefully anyways. So this video is going to be over our Chapter 7 material, which is subgroups. Based on the emails that I'm getting, it seems like this so far has been one of the most difficult chapters for you guys, and I don't know that it's because the material is any more different or any more difficult. I think what's really happening is I'm asking you more what I feel like are conceptual / abstract questions in the homework, and it may be more that we're just not digging deep enough into the definitions to understand what I'm asking. I could be wrong here, but this is somewhat of the impression that I'm getting from the actual questions. So in this chapter, we are going to introduce the concept of a subgroup and begin exploring a lot of the theory behind subgroups. And basically, it may not seem like subgroups are that impressive or special, but what this gives us is an ability to basically find more interesting objects that live in the larger set of the world, in the same way that I assume we're all humans. And in that sense, that's great. And you can think of that as kind of being analogous to our notion of a group. But then there are subgroups of things that are very interesting to think about. So for instance, the subgroup of humans that are musicians or athletes or mathematicians, right? So the idea is we can live inside of something that is interesting in its own right, but then when we really narrow our focus down, it's actually the case that it becomes even more interesting. And so a subgroup is going to just be a smaller group living inside of a larger group. So it is a group in its own right. So really we can think of it this way. The set on which the larger group is defined, then a subgroup is going to be a subset of that larger group set. Remember, the definition of a group gives us that there is a set, a binary operation, and then some properties. And so before we do all this, we're going to reanalyze our notion of Cayley diagrams and mention another property that we overlooked before, and this property is going to be called regularity. So let's start with an example. So consider the group D3. All right. So remember, D3 is basically the symmetries of the equilateral triangle, and it's pretty easy to verify, for instance, that if we do a flip and then a rotation and then a flip, this is equivalent to doing a backwards rotation, right? And so this is the kind of path that we see inside of our diagram for D3. And this should have seemed pretty familiar, because basically if I add two more of these guys, then I get that circular type diagram that I keep drawing, all right? And the reason that, and so the idea is this equation here guarantees, because it holds at any node, guarantees that this object here has to appear repeatedly in the Cayley diagram. So starting at any node, we trace out a path that looks like this. It may be stretched or shrunk or rotated, but we still have the blue connections and the red connections going in opposite directions. All right, and of course this is equivalent to saying something like doing a flip, a rotate, a flip, and then a rotate is equivalent to doing nothing, right? Flip, rotate, allows us to go through a full path in our Cayley diagram, all right? And so these algebraic relations, right, so something like this type of expression, which is often present in a lot of these, gives Cayley diagrams a uniform symmetry, meaning that all the other pieces of the diagram look like some sub-piece, okay? So what I mean here is we're going to see, patterns like this that permeate the diagrams, all right? So this is our actual picture of D3, and what you can see is what was on the previous page right here. So if my mouse isn't showing up, it's the only picture that's on this page. Then what it is it's actually the bottom part of this D3 diagram. So for instance, I'm saying that it's the part that goes from R to R squared to R squared F to RF. But similarly, it looks exactly like the situation that's going from R to RF to F to E and back to R, and similarly over on the left. All right, and this is because there's these relationships, these FRFs equal R inverse, they have to hold regardless of the node that I start at, okay? And there's other patterns that permeate this diagram as well. For instance, performing 2 flips undoes everything, and performing 3 rotations undoes everything. All right? And so by definition, we have that a diagram is called regular if it repeats every one of its interval patterns throughout the whole diagram. So I'm giving a very informal definition here because we're not going to be proving theorems along the lines of a Cayley diagram is, or if a Cayley diagram is regular then. So we don't need something very formal. But what this is telling us is really what? That Cayley diagrams are really built from symmetric pieces, meaning I can think of building this entire diagram by deciding on this little tiny FRF equals R inverse block. I can call that my Lego piece. And if I call that my Lego piece, then it's the case that this D3 diagram is just built from those 3 Lego pieces. Okay? So the notion of regularity is that whenever I see a single pattern or algebraic relation, such a pattern is repeated over and over and over again. All right? Now, every Cayley diagram is regular, and so what I mean is Cayley diagrams we're thinking of as being objects that represent groups, and if it represents a group, then it is regular. All right? So any diagram that does not have regularity, we can immediately know does not represent a group, and hence they're not Cayley diagrams. So the 2 figures below are not Cayley diagrams because they're not regular. All right? And so what do I mean? Well, you can really take any of these kind of patterns that send us back to E. All right? So if we go back to the previous page, what we see is anything that kind of circles us around back to E, right? Flipping twice, rotating 3 times, flip, rotate, rotate. These all send us back to E. So if I start at this, if on the bottom left picture, if I start on the bottom left node, if I follow the 4 red paths, so I go right, 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 and then this big loop back to the left, then I end up back at E. And so the idea then is that I should be able to start at any node and follow a path such as this and get back to the original place. The problem is we can clearly see that there's not a lot of these red loops that exist on the diagram, right? And so I don't have the ability to perform these kinds of rotations that bring me back to the beginning. So regularity means that if you can find a pattern, then that pattern has to permeate the actual Cayley diagram. Right? Now I know that this regularity concept is something that's a bit vague, but it's also something, once again, that we're not trying to prove theorems. This is just a notion of that it gives us another property that we can check for with our Cayley diagrams. So now the reason to bring this up is because before we had this original definition of a group that was informal, and I called it unofficial. And the reason for this unofficialness is because that technically regularity has to be incorporated into the rules. Otherwise, we wouldn't be able to actually completely describe a group. So what do I mean? It's actually the case that the previous diagrams here, under our old definitions, would satisfy all 4 of them and could be considered groups. Okay? So what does this mean then? Well, it means that we needed a little bit more to actually have an official group definition. But remember, in Chapter 2, we were really trying to keep it informal. The idea was we wanted to simply introduce the concept of a group. So, long story short, this means if you go back to definition 2.9 and you add the requirement of regularity, then it is the case that we would have an official and rigorous definition of a group. All right. So, and we've discussed these properties before, but this is the first time that we've explicitly spelled this out. All right. So, moving on from regularity, and of course not moving on necessarily because regularity can still be used in this discussion, then we're going to introduce our formal definition of a subgroup. So, when one group is contained inside of another, and so what is implied here? I have that some object is a group. It lives inside of another group as a subset. Okay? So what do I mean? All of the objects in group H are also present in group G, but group G may have more objects. Okay? So that's what we mean by a subset. But in addition, I'm assuming that H is also a subgroup, which means that it satisfies all of the properties of our definition of a group. So in this case, H is called a subgroup, and we have a notation for it, which is really something like H less than G. You can also write less than or equal, and I kind of switch back and forth, but the idea is really, if you see this less than or equal, we're implying that H is a subgroup. Okay? Now, all of the orbits that we saw in Chapter 6 are subgroups. Now recall, what's an orbit? An orbit is you pick an arbitrary element in a group, and then you simply kind of raise it to as many powers as you want, right? So what I mean, if you pick the element g, then you consider g, g squared, g cubed, g to the fourth, g to the fifth, and so on. But you also consider g inverse, g squared inverse, g cubed inverse, and so on and so forth. And the idea is if our group is finite, we know that we can't leave the group by performing these operations. That's what closure means, that if I perform these operations, even if it is an infinite number of times, then I still will remain inside of my group. And so the orbit of a group element is simply the list of all the elements that you can construct, only using that as a building block. Now what I'm trying to tell you though is that orbit is in fact a cyclic group, and since it lived inside of the original group, it is a cyclic subgroup. Okay, so this is something you should think about for yourself. Okay, now, for example, the orbit of R in D3 is a subgroup of order 3 living inside of D3. Now, what happened here, there should be an equal sign right here. So what do I mean? This angle bracket of R equals, in the curly braces, E, R, and R squared. Why? Because if I do R times R, I get R squared. If I do R squared times R, I get R cubed, which is equivalent to doing nothing. And then if I do E times R, I get R. So this is all that I get. Okay? So this is a subgroup of D3 because each of these guys lived inside of that group. But it is itself a cyclic subgroup because why? It has one single generator. Okay? Now, what we can really also think of is this is, let's say, formally. So what do I mean by formally? If we kind of remove ourselves of the specifics, then this is just a copy of C3 because the Cayley diagrams of this cycle is equivalent to the Cayley diagram of C3. So, more or less, we can say that the cyclic group of order 3 is a subgroup of the dihedral group on 3 objects. Okay, so subgroups are just groups that live inside of larger groups. All right. Now, so what are some examples? So, let's look back at D3. So, recall, and by recall I mean, of course, reconvince yourself of this fact. Then the orbits of all of the elements. So what do I have here? So I have each element, E, R, R squared, F, RF, and R squared F. Then I'm going to look at their orbits. So E times E times E, nothing changes. I just get E. We've already computed the orbit of R, which was this guy. Now similarly, if I compute the order of R squared, what do I get? R squared times R squared is R to the 4th. So what do I mean? R squared, and I do R squared again, and I go to R. And I do R squared again, and I'm at E. So I get the same exact group. What about at F? Okay, if I start at F, and then I apply F again, I get E. So I just get these two flips. What about RF? So let's look at RF. RF means perform a red and then a blue. So if I start at RF and I perform a red and then a blue, I end up at E. So all I have is E and RF. Similarly, the same thing holds for R squared F. So these are all of the orbits. All right. Now, each of these orbits is in fact a subgroup of the Cayley diagram. Okay. And so what do I mean? So for instance, we can see lots of things here. So we have this subgroup generated by R, which is this inner circle. And look, there is an outer circle as well. So we have this pattern being repeated. Okay. Similarly for F, we have this EF, just the single blue line, and that single blue line is being repeated throughout the diagram. All right. RF, which is generated by E and then RF. So what do we have? This is this cycle that we were already looking at on the earlier slides when we were talking about regularity. And similarly, E, R squared F, has a similar type of thing. So we have E, R squared F, and then if we perform, if we start at E and then we perform R squared F, and then we perform R squared F again, we get these similar patterns that start to emerge. All right, so it turns out that all the subgroups of D3 are cyclic orbits, but that's not always the case. So what I'm trying to start with a very simple object that has very simple subgroups, but it is the case when you have more complicated groups that their subgroups are not all cyclic, meaning what? There are lots of complicated things we may need to do to build/find all subgroups. All right, so what's another example? Another example is Z2 cross Z2 cross Z2. All right. Now, there's nothing you really need to know about these crosses other than what? I'm basically saying that we have kind of 3 tuples. So what do I mean? You can put a number, comma, a number, comma, a number, and each of these numbers has to be 0, 1, or 0, 1, or 0, 1. Okay? So this also could be thought of as the Cayley diagram for the 3 light switch group. So imagine on your wall you have 3 light switches, and I'm asking you what are all the configurations of the 3 light switches, meaning all of them down, all of them up, the left one up, the middle one up, so on and so forth. Okay. Now, this guy has more complicated subgroups. Now, what are those subgroups? For instance, the subgroup V4, the Klein group, which is the 2 light switch group, is a subgroup right here. So what do I mean? If I take the element, really doesn't really matter how you want to think about this, but this here is a subgroup, right? So the idea is red goes here, green goes here, red goes here, green goes here. So I can go back and forth between them through these kind of bidirectional arrows. And this square here is equivalent to V4 because it's simply just 4 nodes with 2 different colored arrows connecting them. And then what do we see? I have the same square over here, the same square down on the bottom, the same square over on the left, the same square on the back, and the same square on the top. So these things appear multiple times, but this is a subgroup. Okay? And the idea is, how do I know it's a subgroup? Well, I picked an element, and then I followed it. I went green, which send me, so if I start at 0, 0, 1, I follow the green, I end up at 0, 1, 1. Green sends me back. Red sends me forward to 0, 1, 0. Red sends me back. Green sends me forward to the identity. And then red sends me forward to my starting place. So I have a closed cycle, so this is a subgroup generated by 2 different elements now, right? I needed the red arrows and the green arrows to actually generate this entire subgroup. So it's not cyclic, it has 2 generators, all right? So now the key here is not that I'm asking you to compute anything, but just to ask you to understand that this is a subgroup and it lives inside the larger group, all right? So, this V4 requires at least 2 generators, so it's not cyclic. And so, for instance, the 2 generators can be denoted 0, 0, 1 and 0, 1, 0, or equivalently, red line and green line. All right. And the idea is by following all the possible paths, I get these 4 outcomes, which of course lives inside of this giant lattice that I had before. Now, every non-trivial group has at least 2 subgroups. Now, what do I mean by non-trivial? The trivial group is the group that only has 1 element, and it is the identity. So every other group has more than 1 element, and hence has at least 2 subgroups. The trivial subgroup, which is the identity, right? Because if you take 0 and you add 0 to it a bunch of times, you get 0, so it lives inside of the group of, for instance, the integers. And the non-proper subgroup. So proper means it is completely contained. Non-proper means it is exactly the original group. So every group is also a subgroup of itself, right? Which is why on the earlier slide I said, hey, we can use this less than or equal to notation because maybe it actually is the entire group, all right? So, and then of course a little question here is which groups have only these 2 subgroups, right? Well, what that would mean is that there are no kind of cycles that are smaller than the group itself. So for instance, this means that every element is a generator of the group. So this is something moving forward that you kind of will understand, and what should immediately come to mind is something like the integers modulo n, where n is a prime number. All right? So another example is to consider the integers modulo 6, which are just the integers 0, 1, 2, 3, 4, 5. And then of course you divide by 6 and take the remainder. That's your operation when you add them. So the subgroups of Z6 are the following: the trivial subgroup, the non-proper subgroup, and then there are 2 other subgroups. The subgroup generated by 2 and the subgroup generated by 3. And you might say, well, where did 4 go? 4 is actually the same as this subgroup here because why? When I do 4 plus 4 and I divide by 6, I get remainder 2. And then when I do 2 plus 4 and I divide by 6, I get remainder 0. And now I do 0 plus 4, I'm back at 4. So I end up with the same exact sequence. So these are the only subgroups, all right? And the idea is depending, and remember when we draw Cayley diagrams, we use generators. So what you should kind of start to see here is you could ask yourself, for instance, lots of different things, but how could I generate a Cayley diagram not just using the number 1, right? Obviously this is the only generator we need, and we get the cyclic subgroup. So remember, Z6 is equivalent to C6, so this is our expected outcome, the circular cyclic group. However, I could also use 2 and 3 to generate. Why? Remember, my operation is addition. So I already have 0, 2, 4, and 3. So what am I missing? The only thing I'm missing is the number 5, right? I have 0, or sorry, I'm missing 5 and 1. So I have 0, 2, and 4 from the cyclic group generated by 2. And then I have 0 and 3 from the one generated by 3. So the only thing missing is 1 and 5. Okay, so what can we do? Well, for instance, if I'm generating things with 2 and 3, if I add 2 and 3, I get 5. So I already have that guy. And then if I add 2 to 5, I get 7, which is 1 modulo 6. So now I have 1. So I can, in fact, generate the entire group just using 2 and 3. Now, I always tell you to use the simplest diagram, but you don't have to. Using these two, I actually get the outcome, which is the following, which is D3. All right, so the idea is depending on the choices of generators, we get drastically different looking Cayley diagrams. That doesn't mean that one is more or less correct. What it means is different choices can indicate to us different properties of the actual group that we're actually studying. So basically, by studying the subgroups and kind of throwing them together in various ways, we can actually learn more about the structure of Z6. So not only is Z6 a symmetric group, but it can also be thought of as having a dihedral group structure as well. That's the niceness of it. Okay, and the idea is, of course, it's the dihedral group on 3 elements versus the dihedral group on 6 elements because I've used 2 generators that kind of have reduced my freedom. All right. As another example, we also have D4, which actually has 10 subgroups. And the idea is, how did you go through these? Well, I drew the diagram D4, and then I actually traced out all of these objects, and all of them are kind of as follows. Well, in D4, I have the rotations, and of course, I can perform 4 rotations before I get back to the beginning. Similarly, I can do double rotations twice before I get back to the beginning. I can perform flips twice. Anything with flips ends up being, or anything with these kind of single generators that have flips are always of order 2 because the flip reverses things. But then I have these extra subgroups of order 4, which are somehow these double rotations with flips, and then double rotations with something that also looks like a flip. Okay? And then, of course, I have the trivial and then the whole group. And it's actually the case that some of these are repeats in the sense that they're all kind of exact copies of one another. Now, these subgroups can be arranged into a diagram called a subgroup lattice. So what do I mean? So we have the smallest subgroup, which is the trivial guy, and the largest subgroup, which is the non-proper guy. And it's actually the case that all of these, of course, live inside of D4, but some of these live inside of the other. So for instance, what? R squared lives inside of R. Why? Because R performs the entire rotation, and R squared performs the same rotation, but I'm going kind of, instead of taking single steps, I'm taking double steps. So it lives inside of that group. So we can actually draw a lattice diagram that shows how these subgroups live inside of one another. And what does that look like? Well, it looks like the following. So D4 is at the top because it's the largest element. E is at the trivial subgroup is at the bottom because it's the smallest, and it lives inside of everything. So what does these diagrams represent? It means that E lives inside of this subgroup, this subgroup, this subgroup, this subgroup, and this subgroup. But also, since we climb upward in the diagram, E also lives inside of all of the guys above here because I can walk up to it. So the idea is something is a subgroup of something else if I can find an upward path between the two. So what I mean, E is a subgroup of R squared comma RF because I can go up and over. Okay. Similarly, I can go over and up or over and then back left. So there's all kinds of paths to it. Similarly, R squared is a subgroup of R because of the reason I just gave you. But also, it's the subgroup of R squared comma RF and R squared comma F. Why? Well, R squared is one of the generators. And if R squared generates this subgroup, then of course, then having it as a now generator means that this entire subgroup has to live in this guy because one of the possibilities for these generators is to perform just R squared over and over and over again. So I'm hoping this makes sense. So this diagram is basically laying out to me which subgroups live inside of the other subgroups. And the idea is if I have a cyclic subgroup, so for instance this R squared right here in the middle, it's a cyclic subgroup. Any subgroup that has R squared as a generator must contain this entire subgroup by definition. All right. Now the other thing to note is this is called a Hasse diagram inside of your notes, and I think this is one of the questions that you guys had some concern about, and in the homework I tried to walk you through the procedure for actually trying to develop this diagram here. So kind of step one is find all the subgroups, and then step two is, of course, to try and find which subgroups live inside of the others, and then, of course, step three is to draw this in such a way that we have a total connection that is complete and correct. All right, so please take some time to think about this lattice diagram. It's something that's not entirely obvious, so I think you'll have to probably spend some time thinking about it. All right. Now, a terrible way to find all subgroups is what we call the brute force method. So this is here just to let you know that probably the way you've been thinking about doing this is viable, but not correct. Or let's say not, I shouldn't say not correct. It is not a good choice. All right. So what's a way of finding all the subgroups? Well, of course, item 0 is that we have the trivial subgroup and the total or the non-proper subgroup, and we're done. So now item 1 is find all the subgroups generated by a single element. So what do I mean? If G has 4 elements, A, B, C, and D, or sorry, E, and then A, B, and C. Well, I already have the orbit of E, so then what do? I do A squared, A cubed, A to the 4th, so on until I have that orbit. Then I do B squared, B cubed, B to the 4th until I have that orbit. And similarly for C. So basically you can take each individual element and then find all of the cyclic subgroups. And then what can you do? Well, now I can pair all the 2 elements together. So I can do A and B, B and C, and A and C, and then get all of those. And then I can do the 3s. And so basically you can just methodically walk through and then keep making larger and larger, or making subgroups with more and more generators. Okay. Now, of course, this is terribly inefficient because why? It's often the case, for instance, that some of these generators are repetitions. So what do I mean? Consider the set of integers modulo 10. Well, 2 already generates 4, so trying to do things like pairing 2 and 4 together is redundant. Okay. Similarly, 3 and 6 have some repetition and overlap. So the idea is this is terribly inefficient because intuitively I know that there are some things I don't have to perform over and over and over again. So this is one way to do it, but it's not the best way, and moving forward we will try and actually discuss a better way of doing this. So this is just saying what I just said, that there's going to be repeats, and this algorithm works because every group and subgroup has a set of generators, so by considering all possible generators, clearly I would get everything. But we're actually going to see that Lagrange's theorem gives us a much better way of going about this, because Lagrange's theorem tells me which subgroups are not even possible, so I don't even have to consider them. So Lagrange's theorem is very powerful because it tells me what all subgroups can look like. Not that they have to look that way, but what they can look like. And by knowing that, I can eliminate lots of possibilities. So now the next object in chapter 7 are cosets. And cosets are probably something that is throwing you a little bit. But basically the idea of a coset is I can find a subgroup, and subgroups fit so nicely inside of a group that basically it partitions it. So what do I mean? Pretty much it's as follows. If you think of a Hershey bar, think of all the ways that you can break a Hershey bar with a single break. So what do I mean? Only making one bend, right? I mean, maybe you guys don't eat chocolate. I don't really eat it, but I know what a Hershey bar looks like, right? There are 12 individual rectangles that construct a larger rectangle, or maybe it's 9. Yes, 9. And the idea is there are 3 by 3s of these rectangles. So what I'm saying is, imagine you have this chocolate bar and you only want to break along the edges of the rectangles. What can you do? I can't remove a single rectangle, but I can kind of break it at either of the ends, right? Kind of 3 at the top, 3 on the side, 3 at the bottom, 3 on the side. And no matter which of those breaks I make, there are 2 other equivalent ones left after making it. And that's really the notion of a coset. The idea is if I make one of these breaks of a subgroup, then there are things that are the equivalent shape and size of that subgroup that live inside of the group. And in fact, there's an even number, not even, there is a, by even I mean that I won't have fractional sizes left. It breaks it up evenly with these actual cosets. All right, so maybe I've confused you here, but hopefully this is giving you an informal idea. So, what do I mean? So the regularity property of the Cayley diagram implies that there must be identical copies of the fragment that correspond to a subgroup throughout the rest of the diagram. So for instance, if I look at the subgroup generated by F, it's just this little piece right here. So in the first diagram, it's the green and blue highlighted. And what we can see is in the middle diagram, there's another thing that looks just like it, and in the next diagram, there's another thing that looks just like it. Okay? So what do I mean by just like it? I mean that there are two nodes with a blue arrow between them. All right. Now, the leftmost is a group because it has the identity. The middle and the right are not groups. Why? Because they don't have the identity. But look at what I've done. There are 6 elements in D3, and 2 of them are on the left, 2 of them are in the middle, and 2 of them are on the right. So I have partitioned D3 into exactly 3 buckets, right? So if you think of each picture as a bucket, I have 2 elements inside of this bucket, 2 elements inside of the middle bucket, and 2 elements inside of the right bucket. The leftmost bucket is a subgroup. The middle bucket is a shift of the subgroup. So what do I mean? If you take this one on the left, you simply rotate it clockwise by 120 degrees, and now you have this middle object. It's not a subgroup, but it is, in terms of its diagram, it looks the same as the one on the left. Similarly, if I start on the left and I perform 120 degree rotation counterclockwise, then I get the object on the right. So I have partitioned my group. One of the partitions is a subgroup. The others look just like this subgroup, and they completely fill up the group. Okay? So this is implied that it has to happen by the regularity property of Cayley diagrams. But on top of this, this is really the notion of cosets. The idea that I can take a subgroup and then kind of look at all the copies of this subgroup inside of the larger group, and all of these copies will form the cosets of my group. All right? So this is exactly what I'm saying before. By copy, I of course mean a diagram with an equivalent structure. It does not mean that the nodes have the same labels, because that's not true. I mean, if we erase all of the node labels, then everything looks the same. And the idea is, of course, only one of these copies is a group in and of itself, and the other 2 are just things that look like the group in terms of diagram shape, but aren't groups themselves. All right? Now, the elements of these repeated copies are called the cosets. So what do I mean? This subgroup on the left is a coset. This other object that looks like the original subgroup is a coset. And the object on the right that looks like the original subgroup is another coset. All right? So how do I find cosets? Okay? So at this point, we're kind of ignoring our definition of coset for the time being. Okay? So, and so the idea is we want to find all the cosets of some subgroup R or F comma R squared. All right, so inside of D4, okay, so this is the dihedral group with 4 elements. I want to look at the things that I generate with a flip and 2 rotations. And I get the identity, a flip, 2 rotations, and then R squared F, okay? This here should be, in your mind, very much equivalent to V4, or the Klein 4 group, which is the 2 light switch. So this is a subgroup. All right. So what do I want to do? Well, basically, I want to find all the cosets of H, or sorry, all the cosets of D4. And so, or all the cosets of the subgroup H inside of D4. Okay? So, if we use R squared as a generator for the Cayley diagram of D4, then it'll be easier to see the cosets. So what do I mean? So note that D4 can be generated just by rotations and flips, or also by rotations, flips, and double rotations. Okay? So the cosets of H, and so I'm kind of skipping ahead, assuming that you guys have read the notes to understand what a coset is. But this is going to kind of be helpful moving forward. So the cosets of H, which is just F comma R squared R, well, the coset itself, okay? And then here's the idea. If this is a coset, the only thing that lives outside of it, and that's what I'm kind of trying to do, is see what else can I do? What are my other directions? The only thing outside of this is R, so I can think of applying R to each of these elements. So what do I get? E times R is just R, okay? R squared times R is just R cubed. F times R is just RF. And R squared times F is just R cubed F. Okay? Now, the dihedral group has exactly 8 elements. And so what do I have here? I have these 4 elements, and then I have the remaining 4 elements that I've missed. So I have the original subgroup, and I have some copy of it in the sense that it looks kind of the same, right? There are 2 objects that have flips, and there are 2 objects that can be thought of as rotations, where the identity is like a rotation. So I have partitioned the original group D4 into the subgroup H and some shift of the subgroup H. And now since I have the entire group, there are no other cosets. I have completely partitioned it into objects of the same size. All right. Now, the difficult part of cosets is the formality of the language. Okay, so what you should really be thinking about cosets is always there is a subgroup, and then there are copies or shifts of that subgroup. Okay, so what does this represent? Well, the original subgroup H is on the left, this vertical kind of highlighted diagram where I go E to F, E to R squared to R squared F, and then R squared F back to F. So green represents R squared, blue represents F. Now what we can kind of see is there's also another thing that goes blue, green, and this is exactly this kind of hemispheric orbit on the right. Now it's not a subgroup because there's no identity, but it's an exact copy, and it contains the only 4 things that we miss. Okay, so if I erase the node labels, then I actually get that they look the same in terms of their diagram structures. So cosets are simply these kind of objects that as I find a subgroup and I kind of shift it around, everything looks the same. Okay, so hopefully this makes sense. And so you can also see it's not drawn, and hopefully you can see my arrow, but we could think of a different subgroup. For instance, the subgroup EF, so think of you go like this: E, follow the red arrow to R, follow the blue arrow to RF, and follow the red arrow back to F. Okay, this is has 4 elements. Okay, and then the idea is, similarly, I get these other 4 elements. So if I think of this being quadrant 1, over in quadrant 3, I have the other remaining 4 elements that do what? They go, for instance, red, blue, red, blue. So it's the exact same pattern. So I can partition these things with all kinds of subgroup structures. Okay? So this is something you have to take some time to look at and understand that I need to, every time I find a subgroup, anything that's a subgroup, meaning a group in and of itself, okay, then I can basically find copies of that diagram structure inside of the Cayley diagram. And the kind of all of those copies that I find, right? So if I think of this as a copy, and this quadrant 1 is a copy and quadrant 3 is a copy, there are no other copies in the sense, I mean, there are other copies, but there's no other copies that partition, right? I can think of quadrant 2 being another copy, but I'm going to double down on E and F, and I'm wanting to avoid that. Okay, so I'm wanting to do shifts that don't have repetitions. All right, so your cosets are all of your shifts that do not repeat. All right, so the definition of a coset is pretty simple. If you find a subgroup, then the coset generated by some element A is simply doing what? Take all of the objects that live in H and multiply them by A. Okay? So in terms of a Cayley diagram, here's what this means. Okay, all of your elements in the subgroup H can be represented as arrows or sequences of arrows. So AH is simply doing what? Start at A and then follow all paths in H, right? So H would probably have something like the identity. So A times the identity is just A. Okay? Then maybe H has something like an arrow called B. So then what would I do? I would start at A and I would follow the arrow that's equivalent to B. And the outcome is now in the coset AH. So I can perform this over and over and over again. So going back here, okay, so you can kind of see I'm claiming that this subgroup RH is simply take all the elements in H and perform a rotation. So what can I do? So start at E and perform a rotation, which means what? Follow a red arrow. And that gives me R, which over on the right is highlighted. Start at F, perform a single rotation, which is a red arrow, and I get R cubed F, which is in fact highlighted on the right diagram. Start at R squared F. When I perform a rotation, which is red, I get RF, which is highlighted on the other diagram. Similarly, start at R squared and perform a rotation, and I get R cubed. So by starting at each of the elements in H, right, or I mean we kind of went backwards here, sorry. I was going the other direction. So what I'm saying is start at R every time. All right, hopefully I didn't confuse you with this kind of backwards description. We have a level of commutativity here, which is why I can do that. Starting at R, I can perform E, which does nothing, so I get R. All right. I can also perform an F at R. So starting at R and performing a flip gives me RF. Okay. I also have to do an R squared. So starting at R and performing 2 rotations gives me R cubed. And then finally, I need to perform an R squared F, which is what? 2 red arrows followed by a blue. So starting at R, I go red arrow, blue, and I get R cubed F. Okay? So with the Cayley diagram, you can start at the node A, and then follow all the arrows that live in your subgroup H. And this will give you, from a Cayley diagram, the coset AH. All right. So another example, consider just the subgroup generated by F in D3. All right. So let's look at the F. So kind of it's not highlighted, but it just goes back and forth, EF, 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 EF. Okay. So let's look at the coset RH, which means what? Start at R and perform the 2 elements of this subgroup, which are E and F. So if I start at R and I perform a flip, I get RF. And if I start at R and do the identity, I just get R. So the actual highlighted diagram is a coset, and it is the coset RH. Okay. And similarly, I could have written this coset RF, H. Why? Since RF lives inside of this coset, basically with cosets you can use any of the representative elements as labels. So what do I mean? If you have the coset R, RF, okay, then you can equivalently write RH or RFH. All right, going back to this previous diagram. All right, so I have here R cubed, RF, and R cubed F. Well, this coset is equivalent to RH, R cubed H, RFH, and R cubed F. Because of this notion of closure, inside of our cosets, I can pick any of the objects in the coset and use it as kind of the representative, the guy that's on the left. Okay, so this is how I can construct a coset starting with the subgroup generated by F. So I have RH, which is a coset, and hopefully similarly you see that R squared H is also a coset. All right, so my 3 cosets are H, RH, and R squared H. All right, now the following results should be visually clear. I'm not proving them, but hopefully you could. Any subgroup H, for any subgroup H, the union of all the left cosets of H is the whole group. All right, so this once again goes back to the idea that the cosets of a group, the cosets corresponding to a subgroup partition the whole group. All right, each left coset can have multiple representatives. So what do I mean by multiple representatives? I mean that I can either write it as RH or RFH, right? So many of these many cosets can have multiple representatives. All right, so specifically, if I have a coset AH and B is in this coset, then AH is equal to BH. All right. All left cosets of H have the same size. Why? Well, I start with a subgroup H, and I multiply by an element that doesn't live in H. So if H has n elements, I'm going to perform n multiplications, and hence the resulting coset will have n elements. All right. So once again, kind of reiterating, cosets, you start with a subgroup, and then you consider all of its shifts, meaning taking all of the elements that didn't live inside the subgroup, and you perform all of those operations by that element. All right. Similarly, and so this is kind of what I've already said, for any subgroup, the left cosets partition that group. Okay, so subgroups can also have right cosets. So what do I mean? I can do right multiplications. And so how does that work? Well, algebraically exactly the same. You take the subgroup F, and if I have R on the right, I simply multiply on the right by R, and I get R, FR. Okay? So, and then of course, this is not equivalent to RH because I have now 2 different sets of elements. And similarly, I can multiply on the right by R squared, and I get R squared RF. All right? And what we can see is the left cosets are different from the right cosets. So these cosets must look different on the Cayley diagram. All right? And so they do. So the left diagram shows the left coset R against the subgroup generated by F in D3. So I have this kind of, so what am I doing? I'm taking, sorry, choking a little bit. So what am I doing? I'm taking the subgroup generated by F, which is what? EF back and forth, and I'm going to perform R. So E gets sent to R, okay? And then similarly, F will get sent where? It'll get sent to RF, okay? So the idea is what? The nodes that the F arrow can reach after the path to R has been followed. Okay? The diagram on the right shows the right cosets, which are what? Perform right multiplications. And so these are the nodes that R can reach from each element in F. Okay? So the idea is what? RF is start at R and perform either the identity or perform F. Okay? So R is this node here, and so I perform F to get here, and I perform the identity to go nowhere. The right cosets are what? From each element in F, E and F, perform a rotation. All right? So we can see that they look different, and the order of operations matter because remember, not every group is a billion. All right, so left cosets are start at the node represented by this element and perform all the paths in this subgroup. The right cosets are consider all the nodes in this subgroup and simply perform R. All right, so both give me cosets in different ways. They both, for instance, the right cosets, you can prove the same theorems here. The union of the right cosets is the whole group. Each right coset has multiple representatives. All right cosets have the same size, and all the right cosets partition the group. So we have the same exact theorems, it's just different ways of describing the group. All right, so left cosets look like copies of the subgroups, whereas right cosets can seem very scattered. And the reason for this is because we adopted right multiplication as our kind of definition in Cayley diagrams. If we had used left multiplication, then these kind of observations would switch. All right. So outside of a billion groups, left and right cosets are generally different, even though they are structurally very similar in the sense I just take a subgroup and multiply by various elements. The difference is whether I multiply on the left or the right. Okay. So for any subgroup, we can think of G as the union of non-overlapping equal-sized copies of any subgroup. So what do I mean? If I take H, then basically I can think of all the shifts of H that fill up the group. So this looks kind of like filling up a candy bar. Okay. Similarly, and the idea is they may not always have this kind of regular filling, but the idea is they all will be of the same exact size, and they'll be of an integer number. Okay, so I can think of a pie diagram or kind of cutting horizontally or any other kind of filling with things of the same size, right? And so what you should kind of see here is what I'm trying to emphasize is the left cosets may fill in a very nice way, whereas the right cosets may start to fill in somewhat of a irregular way. Okay, but cosets are simply ways of taking a subgroup and then dividing up a larger group in terms of those subgroup pieces. Okay, so you can think of a subgroup as being your default way of cutting, and the cosets are all of the remaining equal-sized cuts inside of this group. So thinking of you have a pizza, you make your initial cut of the pizza, and then you make all of the other cuts be of that same equal size. Okay, and the idea is it can't be a subgroup if those cuts don't evenly divide the pizza. Okay, so we have lots of competing things: subgroups, cosets, and partitioning, but they all play together, and this is something that you have to carefully go through the notes. Okay, unfortunately, there's not, no matter how much I sit here and describe, cosets are something you just have to get a familiarity with. Okay, and our last example using the integers is probably the best way to get familiar with them. Okay, now the index of a subgroup H of a larger group G is the number of distinct left or right cosets of H and G. They're the same number. So what do I mean? So if I consider the subgroup H of D3, then it's just this block EF. But then there are two other equally sized blocks that partition D3. So the index of H inside of D3 is 3. And this is for the left cosets. Similarly, the right cosets divide up divide up D3 in a different way, but there are still only 3. So the index is the number of copies of H that live inside of the larger group G. Okay? So, and why do we have this object? Because I know that there will be they will evenly divide up the group. So I can ask myself, how many copies of H are in G? Okay? And the number of copies tell me, okay, if there are a large number of copies, then that means that H is small relative to the size of G. If there are a small number of copies, then that means that H is large relative to the size of G. All right. The left and right cosets of the subgroup N, which is generated by R, are the same. So somehow the idea is the subgroup N is nicer than the subgroup H, so its cosets are nicer in the sense that the left and right ones are the same. And so here's a nice theorem that you can prove. If a subgroup H has index 2, then the left and right cosets of H are the same. Now what does this mean? If a subgroup has index 2, then this means that there are only 2 possible places that you can live inside of a group. So listen to this very carefully. Inside of a group G, if the subgroup H has index 2, that means it has divided the group in half. And there are exactly 2 options. You're either in the subgroup or outside of the subgroup. Okay? So what does that mean? There are exactly 2 cosets, the subgroup and everything else. So if the group has index 2, that means that there are only 2 left cosets and 2 right cosets. Since both cosets are built from the same subgroup, then it means that they have to be the same exact partitions. So it's really this notion of that when you have index 2, you've divided it in half, and there's only 2 ways to divide something in half when one of the halves have to remain the same, meaning one of the halves have to be the subgroup H. All right? So this is a nice thing to understand, and it'll be helpful in your homework. So cosets of a billion groups are really a nice way to think of it. And so what I have here is an example of cosets of the integers. So what am I going to do here? So if you have a billion groups, typically we don't write AH, we write A plus H. And remember that's because I said that I'll try and use the symbol plus whenever our group kind of product is a billion. Okay? So for instance, let's consider the group Z with standard integer addition. And then consider the subgroup H, which I've denoted 4Z, which is what? All of the multiples of 4. Okay, so it's a subgroup because 0 is a multiple of 4. And basically the original subgroup itself is just anything that's divisible by 4. So what are your cosets? Okay, so you have all the things that are divisible by 4. Choose an element that is not divisible by 4. For instance, the number 1. Use that to generate your next coset. So what does that mean? Take everything in H, and from the left, add the number 1. So now I get this coset here. Now, take something else that isn't in H, but also isn't the number 1. 2. All right, so something that's not in H and not in 1 plus H. So 2 is not there. So now I'm going to take every element of H and add 2 on the left, and I get this guy. All right, now take any element that's not in H, not in 1 plus H, and not in 2 plus H, so for instance 3, and add on the left of H 3, and now I have this guy. And then you say to yourself, is there anything left? No, I have completely structured the integers. And so the idea is I have all the things that have what? Remainder 0, all the things that have remainder 0 after dividing by 4, all the things that have remainder 1 after dividing by 4, all the things that have remainder 2 after dividing by 4, and all the things that have remainder 3 after dividing by 4. And those are my only options. So cosets can be thought of as taking a subgroup in the integer world and simply adding 1 a bunch of times to each of these objects until I start to get repetition, right? I do 12, negative 12 plus 1 plus 1 plus 1, and then when I add 1 again, I get back at negative 8. So cosets divide up the original group. We take a subgroup, and the idea is the choice of the subgroup is arbitrary, and then we simply perform all of the shifts that don't result in repetitions. So this is the best example of a coset and what you should have in mind. Not that 4 is special, but that the integers are pretty nice because it's something you can understand, and you're basically doing what? Taking everything that's divisible by 4 and throwing it into a bucket. Okay? Taking everything that when I divide by 4 and have remainder 1 and throwing it in a bucket, remainder 2 throwing it in a bucket, remainder 3 throwing it in a bucket. And within these 4 buckets, I have every possible outcome. All right? So now, the right cosets of H are exactly the same because addition is commutative. Okay? Similarly, the reason that I don't write something like 3H instead of 3 plus H is because since H was 4Z, maybe you're tempted to think that I mean 12Z, all the things divisible by 12. Okay? Now, and it's something that moving forward is we'll actually see, look, this is all the things when I get remainder 0, remainder 1, remainder 2, and remainder 3. That looks a lot like Z sub 4, right? The integers modulo 4. Right? If I somehow shrink this down and call this one object, shrink this down and call it one object, shrink this down and call it one object, and shrink this down and call it one object, then really kind of the group of these elements of cosets is itself a group, and it's Z sub 4. And that's actually going to be something we talk about later, and it's called a quotient group, which is somehow the idea of reducing or shrinking our information. So we have cosets. For a billion groups, left and right cosets are the same, but in a billion groups, they're very easy to understand. And so once again, I think that this is one of the best examples to have in your mind when you're thinking of cosets. The difference is for other groups, it could be the case that things aren't so commutative. All right. Now, Lagrange's theorem is really something important, and it was proven by Joseph Lagrange, and it goes as follows. If G is finite and H is a subgroup of G, then the number of elements of H must divide the number of elements of G. So basically it's saying what? So for instance, if the order of G is 10, so G has 10 elements, there are no subgroups of order 3, meaning there are no subgroups with exactly 3 elements because 3 does not divide 10. Similarly, 6 does not divide 10. 7 does not divide 10. So rather than having to check all the possibilities for subgroups when I know that it has order 10, I know that the only possibilities are 1, 2, 5, and 10. So Lagrange's theorem tells us not that there has to be, so let me make something very clear. It says that if something is a subgroup of a group of order 10, then the order of the subgroups has to be 1, 2, 5, or 10. It does not say that there has to be a subgroup of order 5. I hope that makes sense. So what I'm saying here is it tells me what all the possible outcomes are, not that all of these outcomes have to occur. Okay? All right, and then similarly, as a result of this guy, the index of a group is simply the order of the group divided by the order of the subgroup. So if I know that I have a group of order 10 and I have a subgroup of order 5, then the index of that subgroup in G has to be 2 because 10 divided by 5 is 2. So these are very nice computational tools that you should be using in your homework to determine kind of the likelihood or possibilities of various subgroups. All right. Now, a final thing to mention is normal subgroups, and I didn't ask you much about it, but it is mentioned in the notes, and I just wanted to clarify things. So, and let me clarify this. Since I didn't talk about normal subgroups much in the notes, and since I'm not asking you very much about normal subgroups in the homework, that means that this section is not that important. I'm purposely leaving gaps in the information here because I don't want us to be masters of normal subgroups right now. Okay, so I hope I'm not trying to be condescending with this. I'm simply saying this is to fill in the gaps a little bit, but not to fill them in completely. So if you feel like you don't know everything about normal subgroups at the end of this, that is a very good or a very valid way to feel. All right. So a normal subgroup is what? And if you have if H is a subgroup of G, if all the left cosets of H are equal to all of the right cosets of H, then H is called a normal subgroup. Okay? So somehow a subgroup H is normal if all the elements in H commute with everything else, right? So somehow normal subgroups are kind of like the commutative pieces of a group G. All right? So a billion groups, basically all of their subgroups are normal because why? Well, if you think of AH, well, it's just multiplying everything in H by A. But since it's a billion, that means I can switch the order for free, and that's just the definition of HA. All right, so normal subgroups, all right, basically we have kind of the converging of cosets and subgroups here. So a subgroup is normal if all of its left and right cosets are the same. So what do I mean? So not all of them, but I mean if you fix an element G, then the left coset, so the coset little gh and the coset h little g are the same. And this is true no matter which G I choose, okay? So it's not saying if I put G1 here and G2 here, they're the same. That's not what it's saying. It's saying for any fixed G, I can move G freely through the subgroup H, meaning that everything in H commutes with everything in G. Okay, so normal subgroups are very special, right? If you think of groups being this entire slide, all right? And then we can think of subgroups as being the white space on the slides. So throw away the black borders on the top and the bottom. And then normal subgroups live inside of subgroups. It's kind of this definition little box here. So it's a very special and restrictive property for something to have. All right. So, for example, if we consider the subgroup H, which is just kind of generated, so basically here you don't really know what's going on. We have a group Z3, which is kind of the pairs of numbers, where the idea is they're the pairs of numbers 0, 1, and 2. And when I add two of these objects, I add them component-wise modulo 3. All right? So what do I have here? So 0, 1 plus 0, 1 gives me 0, 2, because 0 plus 0 is 0, and 1 plus 1 is 2. 0, 2 plus 0, 1 gives me 0, and then 3, which is equivalent to 0. So this is a subgroup. All right? And so then the idea is, since addition is performed component-wise, it's the case that no matter what element I add to H, right? So what is H? 0, 0, all right? 0, 1, and 0, 2. It's kind of this blue cycle up at the top. So if I add 1, 0, it simply shifts me down every single time. Okay? And it doesn't really matter whether I add on the left or the right, because addition modulo 3 is commutative. So what this means is basically that performing what? So the idea is if I start, so what is this kind of saying? It's saying start at G, which is 1, 0, and then add everything in H. So add 0, 0, add 0, 1, add 0, 2. All right, so then I get this guy down here. Similarly, H plus G means take each element in H and add G to it. All right, so in each of these cases, I end up with the exact same object. So I haven't proven that it's a normal subgroup. I've simply shown you that the left and the right cosets are equal. I would then need to take every single other object in the group and do the same thing to prove that it was normal. Now, so since subgroups of abelian groups are always normal, then pretty much we're always interested in subgroups of non-abelian groups. So, and we're talking about normality. So a way to visualize the normality of the subgroup N is the fact that the left and right cosets give me the same exact partition. Okay? So that's another way of thinking of it. That if H is normal, then all of the cosets partition it in the same exact kind of structured way. All right? In contrast, this guy's not normal because the left and right cosets look different structurally. So, once again, normal subgroups, their left and right cosets, end up giving me the same exact partition, whereas non-normal subgroups, their left and right cosets give me different partitions. So, just as before, if we have that the index of a subgroup is 2, then it has to be normal. Why? Because there's only 2 ways that I can partition the group then. All right? So these are just special theorems. There are normal subgroups that have a different index from 2, but it's a lot more effort to prove that it is, in fact, normal. So, in our case, it's actually pretty hard to prove that something is normal. So often you're going to try and prove that it's not normal, but just by finding some element that violates it. But another thing that we can know is the following. If I have that it's normal, so if a subgroup is normal, then formally I can multiply both sides, so on the right by G inverse, then this G on this part here disappears, and I get a G inverse on this part. So a subgroup H is normal if every element in H, when I multiply by G and then take the element H and then I undo G, I get back where I started, right? So it's kind of saying, do what? Perform G, perform H, and then undo G. And if I end back up at H, then it's the case that I have a normal subgroup, all right? So the following conditions are equivalent. So if GH is equal to HG, then I have that H is normal. If GHG inverse is equal to H, then it's normal. Or equivalently, if for every H in capital H and for every G in capital G, if GHG inverse is an element of this guy, then it is a normal subgroup. And so it's often the case that depending on the particular group, each of these may or may not be easier or harder to use. So having all 3 of them is quite useful. All right. So all it takes to show that H is not normal is just finding one element H so that this guy here isn't inside of H. All right. Now it's the case that this thing here has a special name. It's called conjugation. But for us, once again, we're not so concerned with that. All right. So the idea here of this last section is simply to give us a little more information on normal subgroups so that we understand them a little bit better. All right. So this is it. So what I want to do now is kind of the following. So looking at homework 3, let me kind of go through and talk you through what's needing to be happening, what you need to do on each one so that it's clear. So in exercise 7.1, which of these three diagrams is a Cayley diagram, and which satisfies all the properties of being a Cayley diagram except for regularity? So what do I mean? So I'm saying, okay, look at these Cayley diagrams, look at these diagrams and tell me which one is a group, meaning which one is actually a Cayley diagram, okay? Then tell me which of these, so the idea is which of these three, could be all of them, could be one of them, could be two of them, could be none of them. So tell me which ones are Cayley, meaning which ones are groups. And then tell me which ones satisfy all of our kind of informal definitions. Think definition 2.9. Which of these satisfies all of those except for the regularity property? And so the idea is here I'm simply looking for two answers, right? These guys are Cayley and these guys violate regularity. Okay, and you can provide me some justification for it. Okay. 7.2, each of these diagrams highlight some nodes. Okay, and so the idea is there is the larger group. So for instance, this is V4, and then I've highlighted the identity and then just the kind of B node. Okay, so this is somehow just a highlighted part. Okay, so I want you to first of all tell me if this is a subgroup. All right, so what does it mean to be a subgroup? It needs to be a group, meaning what? Well, it means it needs to have kind of a predefined list. It means to be that if I perform the actions, I don't leave it. I need to have, or you can even think in terms of other definition, I need to have identities, inverses. But the idea is this guy here is a subgroup because it's a group, right? Why? This is the identity. If I perform B, I end up here. Perform B again, I end up here. So I can reverse B. I don't leave this. This is a subgroup. This guy's not a subgroup because it doesn't have an identity. It is a coset, right? This guy here is equivalent to R times this subgroup on the left. So this is a coset, but not a subgroup. So what I'm looking for here is for you to tell me, all right, this guy, subgroup. This guy, not a subgroup. This guy, not a subgroup. So on and so forth, okay? So I'm looking for you to give me answers about yes or no on it being a subgroup. And by highlighted, I mean the things that are green, and the things, those are the things that are green are the kind of candidates for the subgroup, all right? Number 3, basically, so we have these 5 subgroups, okay? So Lagrange's theorem tells me that the order of a subgroup must divide the order of a larger group, okay? So I know how to find the order of C8. How many elements are in C8? Okay, well, 8, all right? So how many elements in C2? 2. 2 divides 8, so C2 can be an element of C8, or sorry, be a subgroup of C8, all right? It's not guaranteeing that it is, it's saying that it can. Okay, so the idea then is, so what I want is an answer. So which of these cannot be subgroups of C8? So basically you find the order of each of these, and then you need to determine which of those numbers do not divide 8. Similarly for D5. So I'm looking for an answer that says Lagrange's theorem says that these guys cannot be subgroups. I'm not looking for you to say that they can be, I'm saying which ones cannot. All right. 7.4. Some of you guys have asked me about this. What is the orbit of E? So what are all the elements I get when I perform E, E squared, E cubed, dot, dot, dot? Well, I just get E over and over and over again. So here is a subgroup generated by B and C. So this means that everything that lives inside of this can be built from B and C. Okay, so if A lives inside of this, then what do I gain by adding A as a generator? Well, A can already be written in terms of B and C. So this is basically like me writing B comma C comma B comma C. So I haven't gained anything. So the idea is this subgroup is exactly equal to this subgroup. So BC is once again a subgroup, and A is not in this subgroup. Okay, so what does that mean? This guy generates some subgroup, and this guy's not in there. Now, the index of this subgroup is 2. So what does that mean? So if I have a group G, this is exactly 1/2 of G, and its other coset is the exact other half of G. A is not in this subgroup. All right. Now, since I've added A, all right, then what does that mean? So think of it this way: if this is a subgroup H, then because of the index being 2, the group is divided into H and AH. All right. And what does that mean? That means that AH is everything in H except I can multiply by A now. So all of my possible things can either be built from B and C or can be built from A times B and C's. So this gives me the whole group. If A is not in this subgroup and the subgroup's order is 28, what do I know about the order of ABC? Use Lagrange's theorem. And it's just simply, you can't tell me exactly what the order is, you can simply tell me something about the order. All right? So, if the order of G is prime, how many subgroups can it have? Well, if the order of G is prime, so for instance, pretend like the order of G is 7, Lagrange's theorem tells me that all of the subgroups of G have to divide 7. And the only thing that divides 7 is 1 and 7. So, there were 2 subgroups. So, if the order of G is prime, then the only subgroups are the trivial subgroup and the non-proper subgroup. All right. Then, we know that the orbit of any element is a subgroup. So, what is the orbit of any element in a group with prime order? Well, the only things are the identity, or the trivial group, and the non-trivial group. So, if we have the orbit of any non-trivial element, it has to be the entire group G. All right. And then the last one is, how many groups of order P are there when P is prime? Okay, so I'm going to let you think about this one, but really what I'm asking you here is, for a fixed B, or sorry, for a fixed P, how many groups are there of that order if P is prime? Okay, so what you of course have to think about is, what does a prime group or group with prime order look like? All right, now, so the goal of 7.6 is the following. In the notes, I had lots of theorems and results where I did things with left cosets. And the idea is you can prove and observe the same exact things for right cosets. So what should you do? You should open up the notes and look at observation 7.3 and take the logic that I used for left cosets and simply rewrite that logic for right cosets. Okay? So what that means is pretty much you need to justify to yourself that you can rewrite the observations for right cosets. Similarly for theorem 7.7, similarly for this observation, why is the number of elements in Hg equal to the number of elements in H? This was also in the notes. And similarly for 7.8. So there's not a lot of novel work here. You simply are rewording all of the work in the notes for right cosets. All right. Consider the set of integers. All right. And the idea here is consider the set of integers with the operation being addition. If n is an integer, then obviously the forward orbit of that is a subgroup of Z. What does it contain? So for instance, if n is 2, then this is saying do 2 plus 2, 2 plus 2 plus 2, 2 plus 2 plus 2 plus 2, 2 minus 2 minus 2 minus 2 minus 2. Right, so do all the things of 2, and what does it contain? Well, it contains all the numbers divisible by 2. So then explain to me what happens if this is just a general number n. All right, then for which n in Z will the orbit of that element give me the entire group? So which of the elements in Z are generators? Okay. If n and m are both in Z, then generate the orbits of these guys. So kind of look at all the elements that are divisible by n and all the elements that are divisible by m. Then when is the orbit of n a subgroup of the orbit of m? Can this guy also have other subgroups? Well, probably the answer is yes, or it depends on what the value of n is. Okay? So it's either yes, no, or it depends. All right? But the idea is we have a pretty simple object here. And then what subgroup of Z is generated by 2 and 5? So I'm asking you to tell me, what does it look like? What are all the elements? Well, of course, it's all the things of the form 2x plus 5y, where x and y are in Z. But I want you to kind of give me a better understanding of what that that subgroup actually is. And then, of course, the same thing for 4 and 6. Okay. In 7.8, find all left cosets of H and G and then state the index. Okay, well, first of all, what you should probably do is find the index so that you know how many cosets there are. So what do I mean? So if H is the forward orbit of 4 in 20, then you need to figure out what that subgroup is. So what is it? It's 0, 4, 8, 12, 16, 20, which is equal to 0. So 0, 4, 8, 12, 16. So there's 5 elements. So the order of H is 5. The order of C20 is 20. 20 divided by 5 is 4. There are only 4 left cosets. So now I just need to find the 4. So I need to pick things that aren't, first pick something that's not in the subgroup and add it, and then do it again and again. Okay? So my suggestion is find the index and then find the cosets, because the index tells you how many things you're looking for. All right? Now, question 7.9 is explaining how to draw a Haste diagram. So the idea is you put the trivial group at the bottom and the full group at the top, and then you basically arrange your subgroups where the idea is you need to make sure that subgroups are mapped into their larger subgroups that they live inside. Okay? And so then the idea is what I want you to do here is the following. I don't even need you to draw it, just understand it. So why are there no lines among any of these subgroups? So meaning, why is there no line from F to RF? Well, so the question is the subgroup generated by F, is it itself a subgroup of the subgroup generated by RF? Meaning, are all the things in this bucket inside of this bucket? Well, the answer is no. That's why there's no arrows. So there's no arrows because they're not subgroups, right? What is the smallest subgroup of S3 containing both F and RF? So the question is, find a subgroup that has both of these guys and find its size. Okay? What is the smallest subgroup of C5? Okay, so this is no longer S3 that's up here. Or sorry, C5 is right here. So now I'm looking at it. So what is the smallest subgroup of C5 with more than one element in it? Well, there's only one subgroup of C5 with more than one element. And then label each of the lines in these two Haste diagrams with the index of the smaller subgroup in the larger. So for instance, if you wanted to label the lower leftmost line in S3, the one going from E to bracket F, then the diagram would have the number 2, because why? The index of basically is what? Take the order of E and take the order of 2 and divide them, and you get 2. So the idea is the index of E inside of F is 2, so put a 2 there. Similarly, you do it for the rest of these. So for instance, on the leftmost, the order of E is 1, and the order of C5 is 5, so you put a 5. All right. And then on the last one, for each of the following questions, either find a group that answers the question, meaning find a group that is an example, or basically give a reason why it can never happen. So I'm suggesting to you to really use those groups that we learned about in Chapter 6. I'm not expecting you to know things outside of that. So is there a non-cyclic group? Is there a non-cyclic group for which all of so that all of its proper subgroups are cyclic? So what do I mean? You have a non-cyclic group, so it's not one of the cyclic groups. The proper subgroups, meaning anything that's not the identity or the entire group itself. Can you find an example where all of its subgroups are cyclic? Okay, and the answer is yes, you can. Is there a non-abelian group, meaning things that don't commute, for where all of its proper subgroups are abelian? So meaning if I take all of its subgroups, then each of these subgroups are abelian themselves. All right, and so this is one to think about. So I just wanted to walk through this to give you some clarification. Obviously, I'm leaving some gaps in some of them, but hopefully with this, you'll be able to understand completely what I'm hoping for you guys to do on the homework. And of course, if you have questions or if you find more typos, then you should let me know, and I'll do my best to get back to you and fix them.